Okay, today we're going to be looking at tutorial 2A. There's two problems in this tutorial. One of them we see an unexpected application of implicit differentiation, and then the second one an example of optimization in two variables where we use isequants to classify the local optimum. Looking at question 5, we have a utility function. Utility, which is a function of sigma, is equal to eta sigma minus pho over 4 sigma squared, bracket sigma squared minus 4, which describes the preferences of an agent who has an opinion sigma on a claim I, for which there's a level of evidence eta, and pho, which is greater than 0. In part A, we need to find the local optimum if eta is equal to 0. Nice and straightforward. If eta is equal to 0, we will get the utility function equating minus p over 4 sigma squared minus 4. If I now expand the brackets, I will get minus pho over 4 sigma to the power 4 minus plus p sigma squared. As we're trying to find a local optimum, I'm going to differentiate my utility function with respect to sigma. So we get minus p sigma cubed plus 2 pho sigma, and I shall equate this to 0. 0 is equal to minus pho sigma cubed plus 2 pho sigma. I'm going to divide by sigma. When I do that, sigma is equal to 0, so that's going to be one of our solutions. And I'm left with minus pho sigma squared plus 2 pho. I can also divide by pho, and then I'm just left with sigma squared is equal to 2. So sigma is equal to plus or minus 2. So root 2 and then minus root 2. This isn't implicitly mentioned in the question, but I am going to find the second derivative, just see if these points, if these optimum points are maximum or minimum. So let me differentiate this again to find the second derivative. We will get minus 3 pho sigma squared plus 2 pho. If I let sigma is equal to 0, the second derivative will be positive 2p, 2 pho, and pho is greater than 0. So that means 0 is a minimum. If I do the same with root 2, I get the second derivative is equal to minus 4 pho, which is a negative value, which means that this point will be a maximum. That's going to be exactly the same with minus root 2, so this point is also a maximum. Cool, so that's part A done. Okay, so here is question B. We are going to be considering a function which has two variables, eta and sigma, and is equal to the first derivative of our previous utility function. And the question is asking us to sketch the isequants of this function for values of a half, 1, and 3 over 2. So when pho is a half, 1, and 3 over 2. So here we have this function, and when we differentiate the utility function, we get eta minus pho sigma cubed plus 2 pho sigma. I'm now going to let the function equal to 0, so that we get 0 is equal to eta minus pho sigma cubed plus 2 pho sigma, and if I rearrange and make e to the subject, we get eta is equal to pho sigma cubed minus 2 pho sigma. Now let pho is equal to 1, we will get sigma cubed minus 2 theta is equal to n. If we now look at some points, when sigma is equal to 0, eta will equal to 0, so 0, 0 will be one of the coordinates. When sigma is equal to 1, we get eta is equal to minus 1, so that would be another point. And when sigma is equal to minus 1, eta is equal to 1, so here's another point. When sigma is equal to 2, we get 4, which would be somewhere off this graph. So we will get something that looks like this, going through 0, 0, going through this point, and steadily increasing towards that. So this would be when phi is equal to 1. If I make sure to write the coordinates, we get 1, 1, minus 1, minus 1, 1, 1, minus 1, and then 0, 0. If I now let p is equal to a half, we get a half sigma cubed minus sigma is equal to n. So when we let sigma is equal to 1, we get a half. So that would be somewhere over here. So minus a half, 1. If I let sigma is equal to minus 1, we get positive a half. So positive half, minus 1. So that would be over here. If I let sigma equal to 2, we get 2. And if I let sigma is equal to minus 2, we get minus 2. So that's going to be 2, 2 over here, and then minus 2 over here. If I now connect up these points, we get something that looks like this. Not my best curve sketching. So this is p is equal to a half. And then finally, if we let phi is equal to 3 over 2, we get the function 3 over 2 sigma cubed minus 3 sigma, is equal to eta. And when I sub in 1 into there, I get minus 1.5. So that would be over here. Let's do this in blue. And when I sub in minus 1, I get positive 1.5. That would be over here. And of course, 0, 0 is still a common point. And that will look something like that. So that's phi is equal to 3 over 2. So minus 1.5, 1, and 1.5, minus 1. And of course, 0, 0 is a common point for all. Cool, moving on. We now need to give an interpretation of what we can see. So what we see is as the value of phi increases, the agent becomes more responsive to changes in evidence as increasing phi makes a function steeper. Cool. Using the technique of implicit differentiation to find the derivative of the optimal values of sigma with respect to eta at the local optimum you found in part A, and use this to write down a linear approximation of the optimum values of sigma as a function of eta around those local optima. Okay, so from before we have this function which is n comma sigma is equal to eta minus phi sigma cubed plus 2 phi sigma. So from before we have the optimum values when eta was equal to 0. So at those values we had sigma is equal to 0, root 2 and minus root 2. And what this question is asking for, we need to find d theta or d theta over d eta. And what that is saying is how does a change in eta away from 0 change sigma? So if we change eta very slightly away from 0, how is that going to change sigma, our optimum values of sigma. So what we're first going to do is equate this function to 0, because that's how we find optimums. And as we are focused on eta, we're going to express sigma as a function of eta. So we get function eta, comma, sigma as a function of eta, as we are focused on changes in eta. If we now differentiate this, we will get the partial derivative fn plus the partial derivative of sigma times by d sigma over d eta, which is equal to 0. If we now rearrange this, we get d sigma over d eta is equal to minus the partial derivative of eta over the partial derivative of sigma. If we work out now the partial derivatives, starting with eta, we can see that we just get 1, and the partial derivative with respect to sigma would be minus 3p sigma squared plus 2p. d sigma over d eta is going to be equal to 1 over, well, minus 1 from this minus, over minus 3p sigma squared plus 2p, which can be rewritten as 1 over 2p minus 3 sigma squared. Okay, now we're going to use that. So let me just rewrite that on a new page. This is not much space given. So d sigma over d eta is equal to 1 over minus 3p sigma squared plus 2p, or 2 If we now sub in the local optimum, so now sub in local optima points, so sub in 0, root 2, minus root 2. When we sub in 0, we get d eta over d sigma over d eta is equal to minus 1 over 2p, because that goes away. When we sub in root 2, we get d sigma over d eta is equal to 1 over 4p. If I just rewrite this as 3p, 3 sigma squared minus 2 you will see that we will get 6 minus 4p, minus 2p, sorry, which is 4p at the denominator. And we see the exact same thing when we sub in minus root 2. So d sigma over d eta, when we sub in minus root 2, is also 1 over 4p. So that's all there is to this first part. The second part of the question is now use this to write down a linear approximation of the optimum values of sigma as a function of eta around these local optimum points. So linear approximation. So the formula for linear approximation is f of x is approximately f of a plus f dash of a times by x minus a. If we now write it as sigma as a function of eta, we have sigma in brackets eta is approximately sigma a plus d sigma over d eta, given that eta is equal to a, and then n minus a. Okay, so what this is the function at the optimum values of sigma for values of eta. And we found the optimum values when eta is equal to 0. Therefore, a is going to be equal to 0. So we can rewrite this formula again as, we can write this function as the optimum values of sigma for values of eta is approximately sigma 0 plus d sigma over d eta, given that eta is equal to 0, and then eta minus 0. So this is basically saying optimum values of sigma when eta is equal to 0, and this part is saying how changes in eta around eta is equal to 0 changes sigma. So let sigma is equal to 0, we get 0 plus minus 1 over 2p times by eta, so we get as a final answer minus eta over 2p. If we do the same with theta is equal to root 2, we get sigma eta is equal to root 2 plus eta over 4p, and if we do the same with minus root 2, we get minus root 2 plus n over 4p. So this is just me subbing in our values from over here into this equation and getting these answers. And that's part C. Part D is now saying, can you use implicit differentiation twice to find a quadratic approximation to the optimum values of sigma as a function of eta around these local optima? So the second derivative would be worked out by differentiating the first derivative again. And why we need the second derivative is because the quadratic approximation, the formula for it is f x0 plus f dash x0 x minus x0 plus f double dash x all over 2 x minus x0 squared. X0 is basically a, so here I used a for my formula, here I've just used x0. And as you can see, we're going to need the second derivative. And all of this is the exact same as before. So to work out the second derivative, we will need to differentiate this. So we get f, we differentiate the partial derivative twice with respect to n, but this is also a function which has sigma in it. So we need to differentiate this with respect to sigma, and as sigma is a function of eta, we get d sigma over d eta. Now, if we differentiate this, so this is product rule, we will get f, this times two sigmas, because we're differentiating the partial derivative of sigma with respect to sigma again. And because we're differentiating sigma, we get d sigma over d eta. plus this with the derivative of sigma eta. And all of this is going to be times by d sigma over d eta. So that's just this part differentiated. Now we need to differentiate this part. So we get the partial derivative of sigma times by this differentiated, which would be the second derivative. So d squared sigma over d eta squared, and that's all equal to 0. Luckily, most of this cancels out because a lot of these values are just 0. So if I rewrite the partial derivative, and the partial derivative with respect to sigma was equal to minus 3p sigma squared plus 2p. So if we differentiate the partial derivative with respect to eta again, we will just get 0. If we differentiate the partial derivative with respect to eta, this time with respect to sigma, we get 0 again because there's no sigmas here. If we differentiate the partial derivative of the function with respect to sigma again, we will get minus 6 pho sigma. And if we differentiate that with respect to eta this time, we get 0 because, of course, there's no etas there. So what this boils down to is this is 0 plus 0 plus brackets minus 6p pho eta d sigma over d eta plus 0 d sigma over d eta plus minus 3p sigma squared plus 2p d squared sigma over d eta squared is equal to 0. So we can ignore this and we can ignore this. So we get minus 3p sigma squared plus 2p d sigma theta over d eta squared is equal to 6 pho sigma d theta over d eta all squared. I've just multiplied that by that and moved it to the other side. And if I make this, so we get d sigma squared over, sorry, d squared over sigma over d eta squared, we get is equal to 6 pho sigma over d theta all over d eta squared all over minus 3 pho sigma squared plus 2 pho. And now what we have to do is sub in the optimum values of sigma. So if I put a new page in, we get, so let sigma is equal to 0, we will get d theta over d eta squared all over 2 pho, and d theta over d eta when sigma was equal to 0 was minus 1 over 2p. So we get 1 over 4p squared times by 1 over 2p, which is 1 over 8p cubed. So we will be left with sigma as a function of eta is approximately minus n over 2p plus 1 over 8p cubed divided by 2 eta squared. And this will boil down to minus n over 2p plus 1 over 16p cubed eta squared. We need to do the same for sigma is equal to root 2. So d squared over sigma d eta squared. If we look back, we get 6 root 2 pho brackets 1 over 4p all over minus 4p. Yep, so now this and this will cancel out, so we get 3 root 2 over 2 times by 1 over minus 4p, which is going to be equal to 3 over 2 over minus 8p. So we will get, for sigma is equal to root 2, root 2 plus eta over 4p minus 3 root 2 over 16p eta squared. And when we let sigma is equal to minus root 2, we get the exact same thing. So minus 3 root 2 over 8p is what the second derivative is. So we get the exact same answer as that. Except this time it's going to be minus root 2. So minus root 2 eta over 4p minus 3 over root 2 16p eta squared when sigma is equal to minus root 2. Cool. Hopefully that all made sense. If we now move on to question 6, optimization. Consider the function 4 plus 3x plus 2y minus a half x squared minus a quarter y squared plus, I'm going to call that symbol s, sxy, for s is a real number. Find the vector a and the matrix b, allowing us to write this equation in this new form. Okay, x as a vector is xy, and b seems to be a 2 by 2 matrix, so I will write a11, a12, a21, and a22, and a is a vector, so I'm going to say a is equal to a1 and a2. If I now sub this in, you'll get 4 plus a1, a2 dot x, y minus a half x, y dotted with a11, a12, a21, a22 dotted with x, y. If I now work out this dot product, we get 4 plus a1x plus a2y. If we compare coefficients between this and this, we can see that a1 is going to be 3 and a2 is going to be 2. So a1 to 3, a2 is equal to 2. And then with this is a 2 by 2 matrix, and this would be a 2 by 1. This is also 2 by 1. We cannot multiply these two matrices for now, so we must multiply these two first. If I do that, we will get a 2 by 1 matrix, which will be a11x plus a12y and a21x plus a22y. Now I can work out the dot product of these two. So we get 4 plus, I'll use the values this time, 4 plus 3x plus 2y minus a half a11x squared minus a half a12xy minus a half a21xy plus minus a half a22y squared. So x squared has a coefficient of a half, so a11 must be equal to 1. And if we quickly look at y squared, y squared has a coefficient of minus a quarter, so a22 must be a half. Now if we look at the xy coefficients, xy has a coefficient of the symbol which I'm going to call s, and that is going to be equal to minus a half a11 minus a half a21. So that means that a11 and a21 both have to be a11 is equal to a21, which is equal to minus the symbol, because when I sub in that, we get a half s plus a half s, which will equal to s. So that would be minus that and minus that. So that would be our A vector, and that's our B matrix. Demonstrate that the first order conditions are the vector A minus the matrix B dot with the vector x is equal to 0. So to do this, first order conditions is equal to the partial derivative of the function with respect to x, and then the partial derivative of the function with respect to y. And when we do that, just from looking at this function, we will get 3 minus x plus sy, and 2 minus a half y plus sx. If I now separate this, so we get 3, 2 separately minus x minus sy, and then a half y plus minus x. We will then write 3 over 2 minus, if I take out the xy, we get on the top 1 minus 1 and minus s. And then at the bottom, if I swap these around, we get minus s and then a half. So that is the vector A minus the vector B dotted with the vector x. And our first order condition is equal to 0. So that's that demonstrated. For which values of s will there be no solutions to the first order condition? So when we have the vector A minus B dot x, there would be no solutions when the discriminant of B is equal to 0. So we're going to find a discriminant of B. To do that, the discriminant of a 2x2 matrix would be AD minus BC, where that is A, this is B, this is C, and this is D. So we do this times this, which would be a half, minus this times this, which would be s squared. And like we said, when it's equal to 0, there will be no solutions, so we shall equate it to 0, where we get s squared is equal to a half, so s is equal to plus or minus square root a half. So there'd be no solutions when s is equal to plus or minus square root a half. Cool. Hopefully that was useful.